All right, so now we've worked a little bit with series, infinite series, and we've talked about convergence and divergence. So let's take a look at how we start to unravel the question: if a series is not a geometric series, how do we figure out if it diverges or converges? So the book offers us Theorem 7, which says that if the sequence of the a sub n converges, if the series of the a sub n converges, then the a sub n terms must go to 0. Okay, if we're not adding smaller and smaller terms, we can't possibly converge to a finite value. That's the underlying message here. So the Theorem 7 leads us directly to the following test to help us determine if a series diverges. Okay, and there's a subtlety here that we have to make sure we get squared away on. So if we have the series of a sub n terms diverges if the limit as n goes to infinity of the a sub n term fails to exist or is different from 0. So we know it diverges if the limit doesn't exist or is different from 0. And this is not quite the same thing as saying if the series converges, then the nth term goes to 0. So with this test for divergence, what we're testing for is if it diverges, but this cannot tell us anything about convergence. So we can either learn that the a sub n terms diverge, or we can learn nothing from using this test. We can't determine that something converges. So let me take you through an example of that, and I'll show it to you. All right, and we'll see what happens. All right. So for an example, let's use the following infinite series from 1 to infinity of n plus 1 over 2n. Okay? So the test for divergence says that the series will diverge if the limit of the a sub n term is not equal to 0. So let's take the limit. So we're going to take the limit as n goes towards infinity of n plus 1 over 2n. Now as we look at this, as n goes towards infinity, n plus 1 goes towards infinity, and 2n also goes towards infinity. So this is clearly an indeterminate form, infinity divided by infinity. So we've got several methods we've learned to work with that. Let's just take L'Hopital's rule because these derivatives will be really simple to do. Won't take too much fuss. So applying L'Hopital's rule, the derivative of the numerator, n plus 1, is going to be 1 plus 0. And the derivative of the denominator, 2n, is going to be 2. So now, just using our rules of limits, we know that the limit of a constant is that constant. So what we see here is that the limit of the a sub n term goes to 1/2. And the test for divergence says that the limit of the a sub n term diverges if the limit of the nth term one-half, if it's not equal to 0. And 1/2 is not equal to 0. So we pass the test for divergence, therefore it diverges. Okay, so we would write the series n plus 1 over 2n diverges, and we would often write by, this is often called the nth term test. Nth term test. Because we're testing if the nth term goes to 0. Okay, so this is an example. What we found is that because that term does not go to 0, okay, if it is not equal to 0, then it diverges. That's what our nth term test tells us to check. All right, let's check another example. In this example, let's use the infinite series 1 over n. Okay, so now let's take the limit. So as n is going towards infinity, we're going to take the limit of 1 over n. And when we check this limit, we know that as the denominator, n, goes towards infinity, the denominator gets bigger, the value of the fraction gets smaller, so this is going to 0. Okay, now the test says that the series will diverge if the limit is not equal to 0, but it is equal to 0. So this series fails the nth term test. And this is the key piece. When you fail the nth term test, we don't learn anything. Okay? So we don't know anything about convergence or divergence. When you fail the test for divergence, you just fail to learn anything that helps you. And you have to take a different approach to figure out if this series is going to converge or diverge. And it's really an easy mistake to make to say, oh, it fails the test for divergence, therefore it converges. The test for divergence never tells you anything about convergence. It can only tell you about divergence. So you want to be careful about that. All right? So that's how you use that test for divergence. And then once you know a little bit about convergence and divergence, though, we get to take a look at this next little theorem. So let's check it out right here. Theorem 8, which tells us whenever we have two convergent series, we can add them term by term, subtract, multiply by constants to get a new convergent series. Okay, so let's look at how this is laid out. If the a sub n has a sum of a and the b sub n has a sub of b and they converge, so a and b are real numbers, they're not infinite, and they're convergent, then point 1, point 2, and point 3 can all come into play. So let me show you how we can use that. Now let's notice what we have to do though. First we have to establish that the series of a sub n's exists and it converges, and that the series of b sub n's exists, it converges. So we have to do that, then we can reach one of these three conclusions. So let me grab a fresh piece of paper and let's do an example. All right, so our example for Theorem 8, I'm going to use this sum right here. This is how we might use Theorem 8 to answer a question. So if my a sub n was 1 over 3 to the n plus 2 over 5 to the n, and I want to try to determine the convergence here, I can use this Theorem 8 to help me out. Because what I'm looking at there is I might be able to use part 1 of Theorem 8 right here to help me out if I can establish that when I separate those into two pieces, if I can establish that the a sub n part of it, the 1 over 3 to the n, converges, and the b sub n part of it, the 2 over 5 to the n, converges, then I can, once I've established that for up here, then I could reach the conclusion that the sum converges. So basically we're going to split this apart and use that theorem backwards a little bit to see what happens. Okay? So let's start out by checking to see if the series 1 over 3 to the n converges and the series 2 over 5 to the n converge. So let's see if these converge. Okay. So first, let's check our 1 over 3 to the n. And I noticed that this looks like it might be a geometric series. We learned about those in a previous lesson. And if I can write it this way, and that is indeed geometric, isn't it? Where my multiplier, my k, is a 1, and then my ratio is 1/3 to the n power. And so this is geometric. With a ratio that is equal to 1/3, which I see is less than 1. And we know that a geometric series with a ratio that's less than 1 converges, so it converges to a, that's a 1 in this example, over 1 minus r, and so that ends up being 3/2. Okay, 1 minus 1/3 is 2/3, invert and multiply, 3/2. Okay, so that's our a part of it. We've shown that our a sub n's converge to a certain value, capital A, just like in our theorem. So now let's do the same for the b sub n's. And so that's going to be 2 over 5 to the n. And I think that one's going to be geometric also. So let's see if we can rewrite it in geometric form. If I put the 2 at the front, my ratio then becomes 1/5 to the n power. And that is geometric. So it converges. Oh, my ratio, I got to check that. My ratio 1/5 is less than 1. So it converges to 2, that's my coefficient in front, 2, 1 minus 1/5. And so that's going to be 5/2. Okay. So what I've established is that the a sub n's here are a convergent series, and the b sub n's here are a convergent series. So I've done this little side work. So now, by Theorem 8, Part 1, from right here, see, I've shown that my a sub n's converge to a and my b sub n's converge to b, and so my sum of the a sub n's plus the b sub n's, which was my original problem, is equal to the sum of the a sub n's plus the sum of the b sub n's and that is equal to the a plus b, so the 3/2, because the sum of the 1 over 3 to the n's was 3 halves, and plus 5 halves, because the sum of 2 over 5 to the n was 5 halves. And so 3 halves plus 5 halves, 8 halves, that's 4. Okay, so that's how we can use this Theorem 8 to determine the convergence of a sum. You could use a similar strategy if you had a difference. Okay. All right, thanks for checking this one out.